get started. Well, hello everyone and welcome to the tutorial on Hamilton-Jacobi Reachability. My name is Somit Bansal. I'm a PhD student at UC Berkeley working with Professor Clay Coleman. I'm co-organizing this tutorial session with Mochen and Sylvia Herbert, who are here. Our plan for this tutorial is to give a comprehensive overview of Hamilton-Jacobi Reachability theory for the first 40 minutes or so. Then Sylvia will tell us about the toolboxes that are available to compute these reachable sets. And then in the later half of the tutorial session, Mo and Sylvia will walk us through the recent advances in the reachability theory and some of the applications of reachability. Okay. Before I go ahead with the reachability theory, one quick note, we want this session to be fairly informal, so if you have any questions, feel free to interrupt me and ask them. Okay, so let's start with the theory part. The main goal of this section is to give you a sense of what reachability theory is, what is reachable sets, how we can compute them, and perhaps most importantly, why they are useful at all. So here is a snapshot of the high altitude air traffic throughout the United States, where each yellow dot represents one aircraft. And on the left here, we are zooming in on the Oakland Center, which is a particular city in the United States. And the air traffic over the Oakland Center is divided into 5 main sectors. Maybe you're not able to see the sector lines, but these are the pink lines over here. And each of these sectors is currently controlled by a human controller. So each human manages the traffic within each sector. And you can imagine these are aircraft, so these are safety critical applications. So federal authority has actually set a lot of safety standards for these aircraft, meaning that they want any two aircraft to be at least 5 miles apart from each other on the horizontal plane and at least 1,000 feet apart from each other in the vertical plane. But given the complexity of this, air traffic system, a natural question to ask is, can we design schemes to help humans in deciding which of the maneuvers of these aircraft might actually lead to a collision, and if so, can we do something about it? Can we actually avoid those collisions? And over years, there are a lot of reachability tools that have been developed to, or a lot of protocols that have been developed to avoid these collisions or deciding which maneuver might lead to collision. And not only that, a lot of these protocols have also been tested by NASA on the aircraft testbeds. But that is not, another autonomous system where the air traffic control is really helpful or useful is UAVs. UAVs has gone a lot of popularity recently, and their potential applications include Amazon Prime Air, Google Wing, where these companies are hoping to use UAVs to deliver packages. The other applications include aerial surveillance and fire management and so on. Here also, we care about a controller which is safe, meaning that when these UAVs are flying together, they should not collide with each other or the buildings. The controller should be scalable, because these UAVs would fly in thousands and thousands of numbers, and we want to make sure that the controller that we are designing is scalable to such large autonomous systems. Finally, it should be reactive. It should be able to counteract the disturbances like wind when they're flying. So here I'm showing a simulation of 50 UAVs set in the urban environment of San Francisco City in California. The black contours here represents the tall building in San Francisco, and these UAVs want to go to one of these 4 destinations which have been assigned randomly. And what we want to do is we want to design a controller which is safe, meaning that it should not hit any obstacle or each other, and they should reach their destination. And to make matters worse, San Francisco is a very windy city. So the winds are constantly flowing, and we want to make sure that UAVs maintain safety and reach their goals despite these winds. And so this is a simulation where we use reachability-based tools to design these trajectories which ensure that we can react to the disturbances in real time, and 2, we reach our goals safely without colliding with any of the obstacles. For a lot of these applications, we will come back in the later half of the tutorial and tell you more about the exact tools that we are using here. But this is just to give you a very high-level overview of the different applications. Moving away from air traffic control a little bit and going towards robotics, reachability can also be very helpful for a lot of robotics applications. One of the particular problems in robotics which is of prime importance is of motion planning. And often this problem is required to be solved in real time, especially when this robot is operating in unknown environments. And there are robotic planners like RRT, rapidly exploring random trees, which can plan these paths in real time. But the problem with RRT is that the planned path may not be dynamically feasible and or even robust. So what this means is that when you execute this path on the real system, this might actually lead to a collision in the obstacles, for example. So these, the robustness here, for example, corresponds to disturbances for aerial vehicles like wind, or noisy actuators for robotic arms, for example. What we can do though is we can actually use reachability-based tools to plan a robustness bubble around this RRT planner, which makes sure that we can robustly track the planned path by RRT. Let me make it a little bit more concrete. Here is a 10D quadrotor model that we actually want to plan a path for this quadrotor from this starting position to this goal position over here. There are obstacles which are these gray walls over here, which we don't know beforehand. So we have to sense these obstacles in real time and plan our path around them. Now, the thing is, any optimal control-based planner would likely be very slow for this application. So what we do is we actually use an RRT-based planner which sense obstacles in real time and plan a path around them using very simple holonomic vehicles. But then this robustness bubble around the RRT planner, which is this cube over here, takes that path into account and robustify it. And finally, what we get as a combination is a planner which is fast as well as safe. The other application which has got a lot of popularity recently is data-driven control and machine learning. And one of the reasons for that popularity is the ability of machine learning to control a system directly based on the data collected on that system. But for safety critical systems, we also want to maintain safety while we are collecting this data. So here is a quadrotor whose nominal model is available initially. And what we want to do here is we want this quadrotor to track a particular trajectory, which I will show in a second. But when we plan a controller using this nominal model and execute on the real system, the quadrotor drops. The model is not sufficient to control the system, but we use this nominal model along with reachability to plan a safe region for the quadrotor, which kicks in as soon as this quadrotor is about to hit the floor and actually stops the quadrotor from hitting the floor. And then the quadrotor explores in this safe region and collect more and more data. And then as it collects more and more data, it's able to learn a better model of itself and finally able to track the trajectory, which in this case is shown by this green-red curve, and the blue is the desired trajectory that we want to track. And reachability is not really limited to these 4 areas. There are a lot of other applications of reachability. For example, here reachability is used to plan or used to do self-helicopter navigation among buildings, or even to plan safe and physically realizable gates for bipedal robots or for complex robotic tasks like walking and running. Reachability has also been used in medical operations, for example, to design autonomous anesthesia delivery systems, where we want to safely control the depth of anesthesia during the medical operations. And the list really goes on, and here I try to compile the different directions that people are looking into within reachability. And this list by no means is exhaustive, so please pardon me if I miss your name somehow. But hopefully by now I've convinced you that reachability has a variety of applications ranging from air traffic control, biological systems, robotics, and machine learning. At a very high level, reachability is useful for probably 3 main purposes. The first kind of problem that you might be interested in is reaching a goal. So the example of that will be a quadrotor want to go to a particular house to deliver the package, and there is wind flowing, so we want to reach a goal safely. The second could be avoid an unsafe region, where we want to avoid a particular set of states. This could be, for example, the collision avoidance example of aircraft, where we want the 2 aircraft to not come too close to each other. And finally, there could be a combination of both, where suppose a UAV is flying through the city, want to avoid the buildings and other UAVs, but also want to reach its desired goal position. And perhaps equally importantly, we want to do this despite disturbances and adversarial behaviors. So the disturbances here would mean winds for UAVs, for example, or actuator noise or model noise for robotic arms. Okay. So I would like to pause here and see if there are any questions before I move on. Okay. So what we do through the rest of this talk is I will first quickly mathematically formulate the reachability problem. We will see what that means really, and then we will see how reachability problem can be casted as a differential game, in particular a geosum differential game, and how we can then use the tools from differential game to compute the reachable sets. And finally, we will see how we can use reachability to compute different types of sets, which I just gave examples of. For example, you want to reach a goal, or you want to avoid a particular set of states, and so on. Okay. So suppose we have a nonlinear system F, whose state is given by X, and we have two controls U and D. Throughout this presentation, I will use this aircraft collision avoidance example as my running example. So we have two aircraft here, excuse me, blue aircraft and red aircraft. The state here, for example, would be the relative position of the two aircraft and the relative heading between the two aircrafts. The control here are the turn rate of the two aircraft. So U is the control of the first aircraft, which we also call player 1's input or player 1's control. And the D here is the control of the second aircraft, the red aircraft here, which we call player 2's control, also disturbance in reachability literature. And then in reachability problem, we also have a target set, which we will denote by G0 here. For the aircraft example, this would, for example, represent the set of all states that are already in loss of separation. So the set of states that we will call as the two aircraft being collided. For the real aircraft, this distance is 5-mile radius, for example. So you don't want any aircraft to come within the 5-mile radius of the other aircraft. So this would be the set of those states. And then we have a time horizon over which we want to compute something, which I will show in a second. And finally, the mathematical notation for system trajectory would be zeta t, which essentially denotes the system trajectory starting from state x0, when the first aircraft applies control U and the second aircraft applies control D. The reachability problem is essentially to compute the set of all states for all possible actions of the first aircraft, or control actions, which is the blue aircraft here, there is a control of the second aircraft, or the red aircraft, which can drive the system to the unsafe states. Which means that this is the set of all states from which if the red aircraft wants, it can actually collide with the blue aircraft. Now, note that it's not that the blue aircraft is the two aircraft really actively trying to collide with each other, it's just that these are the set of states from which collision is a possibility. Mathematically, we can represent this set as there exists a D, meaning there exists a control of the red vehicle, such that for all actions of the first aircraft, U here, there exists a time at which our system trajectory would enter the unsafe states, or the states that are in collision. And we will soon see how we can compute this set, and eventually this set will look something like this over here. Of course, this is shown in the 3D here because it's a 3-dimensional system state. And here I'm showing a 2-dimensional slice of that set. But really, once we have this set, we can divide our state space into the regions of safe states and unsafe states. In particular, if the red aircraft starts outside the reachable set, then the blue aircraft has a control sequence that it can apply, which would guarantee that it will never collide with the red aircraft, despite the best try by the red aircraft. And on the contrary, if the red aircraft starts within the reachable set, then we are at the mercy of the red aircraft, and no matter what we do, red aircraft has a control sequence that it can apply, which would lead to the collision. And again, the collision here means that the two aircrafts are within the 5 miles of each other. Okay. And there are several ways to compute reachable sets, and here are some of the methods that can be used to compute the reachable sets. Unfortunately, I won't have time to go through a lot of these methods, but in the tutorial paper, we have presented a brief overview of some of these methodologies. In this particular tutorial, we will focus on the Hamilton-Jacobi analysis to compute the reachable sets, and primarily for 3 reasons. The one is that it can handle general continuous time nonlinear dynamics of this system. 2, it can account for disturbances and adversarial behaviors, which is a key in safety critical applications. And 3rd, we will aim to compute the exact reachable set as opposed to some of the approximations of the reachable set, which can be conservative in certain scenarios. Okay, so let's back up and see what we have talked about so far. We talked about the reachability problem, which in words means we want to compute the set of all states for which, for all possible control action, there exists a disturbance action that can drive the system state into the set of unsafe states, which we also call target set. And one quick note here, I have motivated reachability using a collision avoidance example, but that's not the only case where we can use reachability. We can also compute other types of sets. For example, rather than using a set, which means collision, the target set could represent our goal states. So for example, for robotic arm, that could be all the desired set of configurations that you want to reach eventually. And here, for example, it's a quad order that wants to go to this house to deliver the package. And we are interested in computing the set of all states from which we have a control to satisfy our goal. I will touch on these sets again in the last section of this talk, but I just wanted to briefly mention that over here. So next I will talk about how reachability problem can be casted as a differential game, and then how we can borrow those tools to compute the reachable sets. Any quick questions? Okay. So optimal control. So for the discussion of optimal control, I will take out the disturbance for a minute. So it's a single player scenario now. In optimal control, we have a cost function, or cost functional to be precise, which is a function of our state and our control sequences. And we have 2 parts to the cost, which is, the first one is C, which is called running cost. And then second one is L, which is the terminal cost that we will incur at the terminal state. And we have our system dynamics, x equals to f of x and u. And the goal of the optimal control problem is to find the control sequence or control strategy that minimizes this cost functional subject to system dynamics. Traditionally the way this problem is solved is we define a value function, which is essentially the minimum of this cost. So solving the optimal control problem is equivalent to finding this value function essentially. And one particular tool to compute this value function is principle of dynamic programming. So to understand the dynamic programming, suppose that we start from the state x0 and we want to solve the optimal control problem. And magically, somehow I know the state trajectory which gives me the optimal cost, which I'm denoting here by zeta t. Now, dynamic programming principle says that if you take any intermediate state on this trajectory and would like to solve the optimal control problem starting from this state for this much horizon, which is capital T minus delta, then this trajectory would still remain optimal for that optimal control problem. So among all these 3 trajectories or many others, the orange is still the optimal trajectory. What this allows us to do is to compute value function in an iterative fashion, starting backwards, and we can decompose value function into the sum of 2 parts. The first one is the running cost incurred along this trajectory, and then the second part is the value function starting from this state. And to compute this recursively, what we need to do is we need to know the value function at the terminal time, which we know already because this will be simply the terminal cost of our optimal control problem. And this equation right here is called Hamilton-Jacobi equation. It's the equivalent of Bellman equation for continuous time systems. There are 2 equivalent forms of Hamilton-Jacobi equation. The first one is called integral form. If you just rewrite this equation, then you can also get the differential form of Hamilton-Jacobi equation, which we will primarily deal with in this tutorial. To summarize the optimal control part, optimal control, at least for this tutorial, is equivalent to solving a final value Hamilton-Jacobi PDE. Now note that this is just for this tutorial. There are a lot of ways to solve the optimal control problem. Okay, so now let's move on to differential games and introduce our second player. So now our dynamics contain U and D, player 1 control and player 2 control. And just to remind you, player 2 control we generally denote by disturbance in reachability literature. And now we have a cost function which is a function of both U and D. So essentially, what we do, in this particular case, we are interested in the zero-sum differential game. What that means is that player 1 wants to minimize this cost functional, and player 2 wants to maximize this cost functional, or vice versa. This is just one example. And really, these games were studied heavily by Rufus Isaacs in 1960s when he was working at Rand Corporation. I think his time was overlapping with Bellman, and so he was studying dynamic programming, and Isaacs was studying differential games at that point. Anyway, so here again, we want to find the control sequence which, from U's perspective, that minimizes this cost functional, and we want to find the control sequence from D's perspective that maximizes this cost functional. So whenever there are two players, or whenever there is a game in general, we have to first talk about the information pattern in this game, meaning what information each of the players has access to because that can change the outcome of the game completely. Here we are interested in non-anticipative strategies for player 2. Now this is a mathematical definition of non-anticipative strategies, but what really this means is that the future actions of player 1 doesn't affect the current action of player 2, meaning that this game is in some sense evolving continuously. So those two players are playing continuously. It's not that player 1 is playing first and then player 2 is waiting and then player 2 will play. So that's essentially what we mean by non-anticipative strategies, which is a fair assumption to think about most of the games that we are interested in. So okay, so now that we have the information pattern defined, we can define the value function of this game in a similar fashion as we define it for the optimal control problem. So this is VXT, except that now there is an additional maximization with respect to the strategies of disturbance. So here capital gamma T really represents the non-anticipative strategy set. And what we want to do is we want to find the control sequence that minimizes this cost function, but also the strategy of disturbance, non-anticipative strategy of disturbance that maximizes this cost function. Okay. And really the analysis follows similar to that of optimal control. Now we can also solve this, we can compute this value function by using the principle of dynamic programming. In this case too, we get a final value Hamilton-Jacobi Isaacs PDE. The only difference is that now we have an additional maximization in the PDE. Okay. And once we can find the value function, we can compute the optimal action as really the argument of this thing over here. And similarly, we can compute the optimal disturbance by doing the argmax over here. Okay. So a lot of math in the past few slides. So let me just pass that one by one. We talked about optimal control and zero-sum differential games. In optimal control, the dynamics consist of a single control U and state X, and in zero-sum differential games, we have two controls, U and D. Both have some sort of cost functional. In the optimal control, the controls want to minimize this cost function. In zero-sum differential game, one player wants to minimize, the other player wants to maximize. We can define the value function. Once we can define the information pattern in the zero-sum differential game, in this particular case, we talked about non-anticipative strategies. We simply mean that player 2 cannot anticipate the actions of player 1. And once we do that, we can define the value function, which in both cases we can compute by solving a PDE. In the case of optimal control, that's called Hamilton-Jacobi PDE. In the case of zero-sum differential games, that's called Hamilton-Jacobi Isaacs PDE. Here, the only difference is that this term only has single optimization, which is with respect to control. In the case of differential games, of course, there are two agents, so we have to perform two optimizations. The one is minimum, the other one is maximum. And finally, once we have the value function, we can compute the optimal action in a similar way in both cases. Question?
You okay if you ask in between?
Yes.
Okay. Can you compare the complexity of the two PDEs? Is it like one is it just like higher dimension because you have an additional input, or is it significantly more or fundamentally more complex to solve the Hamilton-Jacobi equation versus the other one?
Yeah, that's a good question. So in terms of dimensionality, they are both of the same dimension, and that really depends on the dimensionality of state. What's complex about this PDE though is to perform this optimization right here. So for a lot of the reachability analysis, as Sylvia would tell us later on, we rely on computing this Hamiltonian. Because the tools really just solve this PDE. But to solve this PDE, you have to give it Hamiltonian, which itself involves one optimization. Now, if you can perform the optimization, in both cases, they are of the same complexity. But of course, this min-max optimization is much more harder to perform. So the complexity comes really from there.
Okay. Thank you.
Harsh.
I'm guessing there's something implicit or explicit about the order in which you're doing the max and the min, that you can't swap them. So it's a situation that what's happening is that the aircraft or whatever associated with you perform some action to minimise something, and then instantaneously the other aircraft reacts to it. Is that how the problem's set up?
Exactly. That's a very good question.
You can't change the order of the max and the min without.
It depends on the kind of problem that you're interested in.
Yeah.
But here, what I'm doing really is by using this min and max order, I'm giving player 2, in this case disturbance, an instantaneous informational advantage over player 1, which means that it can perform the optimization after looking at the current action of player 1. And that is because in reachability, we are interested in worst case scenarios. So for example, if the U here is aircraft 1, again, just in our running example, and D represents aircraft 2, then what we want to find is, despite the best try of player 2, can we remain safe? And so essentially, this maximization captures that aspect, or this particular order captures that aspect for us. Any other questions?
You talked about the disturbance being one agent. What if the disturbance is multiple agents?
Okay, so I think if there is so here I'm certainly talking about zero-sum differential games. If there are multiple agents whose goal is same, for example, so suppose there are 3 agents who really just want to maximize a single thing, then in theory you can interpret that as a single agent whose D could be multidimensional in this case, for example. But if there is an agent, if it's a multi-objective problem, then that's not something what I'm dealing with here for sure. Okay, so to summarize, we talked about reachability problem, and then we briefly talked about optimal control and differential games. In the crux of that is that we can solve a differential game by solving a final value Hamilton-Jacobi experiment, which looks something like this. And really, this should be a partial. So my apologies for that. But the idea is that it should be a final value PD that we need to solve the differential game. Okay. So next let's take a look at how we can use.
So if you change the order in the min-max thing, does it preserve the Hamiltonian, or it's a special? You can in principle get 2 Hamilton-Jacobi PDs, right?
Yeah.
Well, with the exchanged order. So do they coincide, or?
It depends on the problem. In the cases where suppose my dynamics are control affine in both U and D, then you can imagine that order of min and max doesn't matter. In the cases where suppose they're multiplicative, it really matters, right? Because whatever you do, I can just literally change your direction, for example. So if it's an aircraft and you go in this direction, I can simply just turn this way, and that would totally change the outcome of the Hamiltonian. So it depends on the problem. But yes, those 2 Hamilton-Jacobi equations in general represents 2 different types of sets. And we will talk about one of them.
If we reflect back to the definition of this reachability problem, it seems like the order of min and max is, because you're saying that for all possible constructions, wouldn't that mean that, and there exists one different disturbance action, then, but in the slide you just described, you're choosing the best disturbance that would maximize.
For the zero-sum differential game?
Yeah.
That's exactly right. Yeah, but I will, in the next few slides, I will exactly explain how we will use those tools to exactly solve that problem.
Okay.
I haven't yet solved that problem. So far I've only explained how we will solve differential. Okay, so going back to reachability now, just to remind you, the problem that we're interested in here is that we have a set of unsafe states, which is this dark brown set over here, and we want to compute backward reachable set, which is this light brown set over here, which means that for any state in this set, there exists a disturbance action so that for all control actions, it can still drive the system state to the unsafe set. And to do that, what we can do is we first define a particular level set function, or L of x, such that my target set can be written as the sub-zero level set of that function, meaning that my target set is given by the set of all states where this function is negative. And this can always be done, by the way, by, for example, using a sign distance function. And then what we do is we define a zero-sum differential game between control and disturbance, where the cost functional is the minimum of this function L over the entire trajectory. This is my cost function. We will see why that works, but I'm just going through the process of defining the differential game which will give us the reachable sets. Again, it's a zero-sum differential game, so one would minimize, the other would maximize. And what can be proved then is that the reachable set is given by the sub-zero level set of the value function of this differential game. And that's why it's called level set approach. Because I'm encoding my sets as the sub-zero level set of a different function. Okay, so this seems pretty confusing. So first let's take a look at it, what it means or how we will compute the reachable set. So again, we have our target set of unsafe states. To visualize, let's consider a one-dimensional slice through that target set. So what we are first doing is that we are defining this function L of x, which actually is negative inside the target and then the positive outside. Now we will define the differential game as before and we compute the value function of that differential game. Here I am showing one of the slices of that value function. Again, value function can be computed using Hamilton-Jacobi I6PD because it's a differential, zero-sum differential game. And once we have that value function, then the backward reachable set is really just given by the sub-zero level set of that value function, which is that the slice is over here and the backward reachable set is over here. Okay? So that's good. I have an algorithm or I have a method to compute the reachable set, but why does this work? So let's try to look into that a little bit. So if you recall, this is the cost function I defined. And let's see why this cost function works. To visualize this, let's consider three different levels of that function L that I'm defining over here. And before we start this analysis, just a reminder that zeta here is the trajectory of the system at time s, starting from the state x. Okay, so going back to L, recall that the target set is given by the sub-zero level set of L. So this is my unsafe state here, unsafe set here. And these are two other levels of this function. So Lx equals to 1 and Lx equals to 2. Now consider a state x. And suppose we apply some control action and some disturbance action, and this is the corresponding trajectory we got from starting from this state and applying control action U1 for the first aircraft and D1 for the second aircraft. And let's see what the cost function will look like for this particular trajectory. So we start from roughly like 1.8 L. Then our L decreases, and it becomes negative once it hit the unsafe region. And then it exits the unsafe region and it again starts increasing and probably something like 2.5 or 3 here at the end of the trajectory. And the minimum over this entire trajectory is achieved when the trajectory was passing through the unsafe state. And in particular, the value of this cost function for this particular trajectory would be negative. So essentially, what we can do is we can actually just look at the cost value for trajectories and decide whether that trajectory ever hit the unsafe region or not. In particular, if the value of a trajectory is negative, then we know that it actually must have passed through the unsafe region. And that precisely, if you recall, was the definition of the reachable set, which is that the set of all states for which the value is negative. And that's the key intuition behind the level set approach. Okay. Cool. So going back to our Air 3D example, or the collision avoidance example between two aircrafts, recall there were two aircraft. The unsafe region was the 5-mile radius around the first aircraft. And here, what I'm showing on the right-hand side is the target set in 3-dimensional space. So this is the x-axis, this is the y-axis, which by the way is the relative state between the two, or the relative position between the two aircrafts. And psi here, which is the relative heading. And this is my target set, which is simply the sign distance function. So it's negative inside the cylinder and positive outside. And then what we do is we cast this zero-sum differential game as I described in the previous few slides, and then solve the reachable set using level set toolbox, which Sylvia will talk about probably in 10 minutes. And here is what the reachable set computation looks like. This is the reachable set computation over time. And this final set that I'm showing here is the converse set. So it's the infinite horizon reachable set. Okay. So to summarize, what we saw is that reachability problem can really be casted as a zero-sum differential game, and then we can borrow the tools from the differential game using the level set approach and just solve a Hamilton-Jacobi Isaacs PDE to compute our reachable sets. Okay, before I move on, any questions?
I just want to add a comment on the cartoon which you had. Could you go back to that slide?
This one?
The one before. So here, the reason why we had max and min is because interest is sub-levels.
Yes.
The moment you make max and min of the value function, you end up with that for all control there exists.
Yeah. So this goes back actually to one of the questions that you asked, which is that here, okay, maybe I should go here. If you see here, is in differential game we talked about min and max. Here I'm doing max and min. That's because here my control wants to keep me out of the unsafe region, where my value is really negative. And that's why control wants to maximize the value of L, and disturbance wants to minimize the value of L. But the idea is exactly the same. Yeah.
Oh, sorry.
Yeah.
Does the formulation change order to the techniques you're going to talk about? Are they affected if the dangerous region, the geometry of the dangerous region depends on the disturbances?
Sorry, can you repeat your question?
So if you have aircraft, your aircraft 1, it's got you currently have it's got like 5-mile radius, and aircraft 2 gets inside the 5-mile radius, that's bad. What happens if the radius was named and changed with the disturbances? So actually worse than the radius change, the whole shape change. Does that affect? So for example, if the aircraft, if this is my aircraft and this is the other aircraft, if I was flying like this, the radius might be very big, but if I was flying like this, the radius might be very small. Is that?
Yeah, and so that is exactly why this set is a 3D set, right? And you can see that this set is not symmetric across different angles. So what you just told me is the example of different headings. So for example, the relative heading here is 90 degrees, and the relative heading here is 0 degrees. So you can see the unsafe set is actually biggest when the heading is 0. 180 degrees in this case, yeah. And that's exactly because of the intuition that you said. Does that answer your question?
Possible.
You mean that the unsafe region can change dynamically? That's
Yes.
the question?
Yeah.
Oh, I see. Yes, it can. We will talk about one of the particular flavors of reachability, which is time-varying reachable sets.
But it's not just varying with time, it's varying with the actions of the other player.
So I think I think a simple answer here would be we're assuming the worst case disturbance. So just saying if the other player plays to our most disadvantage, then we will still be able to have control to ensure safety. If they do not apply the worst disturbance possible, then of course we know that we still have a control to keep safety. Does that answer your question?
Maybe.
Okay. Well, please
We'll
contact
see,
us.
yeah, we'll see.
Yeah, please let us know like after the tutorial. We'll be happy to chat.
So, in the interest of time, I would probably move a little bit quickly through this section. But here, really my goal is to give you a glimpse of different types of sets that you can use, that you can compute using the same theory that we talked about. So far we have focused on something called avoid set, where target set represents the set of states which we want to avoid, which is kind of a little bit counterintuitive. We are calling it target set, but this is really the set of states that we want to avoid. But we can talk about other set of states. For example, reach set, where we want to reach a particular set of states. Again, this is the example that I gave earlier, is that a robotic arm may want to reach a desired set of configurations. So this dark green set over here will represent all the desired configurations that we want to reach. And this will be the set of states from which we can reach those desired set of configurations. And then we will talk about forward reachable set, which is the set of states that we can reach from a given set of states, rather than to a given set of states. And I will give you concrete examples of each of them. So in avoid set, we talked about aircraft collision example. So I probably won't repeat that. So let's talk about reach set. So in reach set, the quad rotor, for example, want to reach a particular house. So my target set or my goal set of states is this. And then the wind is flowing, and we want to compute the set of all states from which we can certainly reach the house despite those winds. So essentially this set of green states is my goal satisfaction states. So from these states I have a controller which would reach my goal positions. Similarly, for forward reachable set is the set of states from which is the set of states that you can reach from a given set of states. So here is an example of safe landing aircraft. So the goal here is to actually find a safe landing spot for an aircraft which has actually lost one of its engine. Is that the problem? Yeah. So it's lost one of its engine, and then we want to just safely land for a particular position. So we want to know what are all the positions that I can reach on Earth, starting from my current position, and which of them are then safe. So that's what we will compute. In that case, we will compute a forward reachable set, which is the set of states that I can reach from my current state. And really, we can also write these definitions mathematically, which I think I will probably not go through in too much detail. But the idea here is that we want to seek a disturbance action for all control actions, such that we go to the unsafe state. Here we seek for all disturbance action there exists a control action which will take me to the goal state. And then here is the set of all states that I can reach from my current state. And really, these are just a little bit shuffling of for all and exist operators. And in the final stage, or finally, these all sets can be computed using the Hamilton-Jacobi ISXPD. They will just look a little bit different in terms of the Hamiltonian.
What if you have a place you want to go and also a place you want to avoid?
Awesome. So this is what we call reach avoid set. Which is the set of all states that we want to compute the set of all states from which we can reach a desired set of states while avoiding some other unsafe set of states. And the perfect example of that will be the UAV application that I showed earlier, where a UAV wants to go to a particular house, but it doesn't want to hit the buildings on its way. And this is what something a set will look like. And this is the example. I'm moving ahead of myself. But really, the mathematical definition of this set is exactly the same. So this part is exactly the same as the goal state. But now there is an additional part which says that for any time you shouldn't be hitting my unsafe state. And the good news is that this set can also be computed in a similar fashion. It's also equivalent to solving a single Hamilton-Jacobi ISXPD. And cherry on the cake is that these sets can be time varying. Both my target set and my avoid set can be time varying and it is still a single Hamilton-Jacobi SXPD that we require to compute these sets. And indeed, for the UAV application where we saw that San Francisco example where 50 UAVs are flying, we were indeed using time-varying reachability. And Sylvia will talk about that later on more. Okay. So, maybe before I summarize, any quick question on these sets?
For the time varying case, you probably change the value function, you make it time dependent, or?
Yes, the value function will be time dependent. My target function will be time dependent, as so is my avoid function will be time dependent.
So in the static stationary case, I imagine that you can always find the value function, but let's say I give a dynamically changing set, can I always choose a good time varying value function? Is it possible to do?
Yes.
Okay.
Okay, so let's summarize this session. And then the first takeaway from reachability is that we see how it is an important problem for safety critical systems. We saw a variety of applications of reachability ranging from air traffic control to UAV control to robotic planning and to machine learning. The second thing is we can compute these reachable sets using level set approach, which essentially inherit the tools from zero-sum differential games to compute these reachable sets. And ultimately, computing the reachable set is equivalent to solving a Hamilton-Jacobi SXPDE using the level set approach. Finally, we see how we can compute different types of reachable set depending on the problem that we are dealing with. We talked about reach versus avoid set, where we want to avoid a particular set of states or we want to reach a particular set of states. We talked about reach avoid, which is we want to reach a particular set of states while avoiding other set of states. And we talked about forward versus backward reachable sets. And all of these sets can be computed in time-varying fashion. So that's all for the first session. If you have any questions, I'm happy to take them now.
So how much can you scale? So how many agents can you compute effectively? Like, say, 10,000 or I don't know.
Again, depends on the problem. If you want to compute the joint reachable set for 10,000 states, you can't do that because ultimately the underlying principle is dynamic programming, which suffers from curse of dimensionality. And in fact, Moore's talk is mainly around that theme. There is some recent theoretical advances to overcome the curse of dimensionality for certain kind of systems. In some other cases, you can impose some sort of structure on your problem to overcome that curse of dimensionality, which we will also talk about. Okay, so I think I will probably ask Sylvia to now start her presentation because probably we are running out of time. But
thank you so much.